Okay, so now we're going to look at how energy is dissipated in electronic circuits. And we're going to come across something called Joule's law. Now, to understand Joule's law, what we're going to do is look at what voltage actually is. So let's remember that. Voltage is a potential difference. Now, if we have an electric field somewhere, so suppose we have a charge at rest in this field, and we let it go. If it's a positive charge, by convention, it's going to go in the direction of these arrows. And going from point A to point B, say, it's going to pick up some kinetic energy. Conversely, by the work-energy theorem, we want to take it from B to A, we're going to have to do that same amount of work to get it there. Now, potential, or electric potential, is a way of keeping track of this potential energy. Namely, electric potential is the work needed per charge to go between 2 points. You can think of it as energy per charge. Its units are not joules, it's not an energy, it's an energy per charge. And the units of that is volts. Okay, let's think about that for a sec. Suppose we have a cluster of charges, and we're going to let them all go one by one. Every time we do that, we're transferring a small amount of energy from A to B. If we do it one by one, we're trading different blips of energy, one after the other. Okay, imagine we had many charges now. So many, in fact, that it's like a fluid flowing. What we're going to get is an energy per unit time being transferred across this voltage. What's an energy per unit time? That's a power. So let's look at the power, the energy per time. Well, it's the number of charges we have times that voltage that it goes across. That's QV for all of the charges divided by T. Now let's rewrite this in terms of known quantities of electronics. We have power is equal to energy divided by time, and that's the same as charge per time times energy per charge. Now charge per time, we know what that is, that's current. Energy per charge, that's voltage. So power is current times voltage. Every time a current is moving across a potential difference, energy is being transferred. We have a power. And this power is current times voltage. P equals IV. That's Joule's law. And it's true in general. So for an example, let's say I have a light bulb, a 40-watt light bulb. In fact, I do. Here we have a 40-watt light bulb driven by the 120 RMS coming from the wall. We can use Joule's formula to tell us what the current is. I'll attach a current clamp, which will actually measure the current going through the wire, and we'll see if everything is consistent. Okay, so we have times 10 multiplication on there, and we see that when we flick the switch, we're going to about 3.3 times 10 to the minus 1 amps. So that actually makes perfect sense. Great. Now this power is equal to current times voltage is true in general. But if we have something additional, if we know that we're dealing with resistors here that obey Ohm's law, we can rewrite it in a couple of different ways. Let's have a look. So if we have power, which is current times voltage, we can plug in I is equal to V over R. And therefore the power across a resistor is V squared over R. Similarly, let's plug in I times R for the voltage, and we have power is equal to I times R, which is I squared R. So we have three equivalent forms for resistors. P is equal to IV, P is equal to V squared over R, and P is equal to I squared R. So for example, let's say we have a 5-volt battery and we're going to drive current through a resistor R. How much power are we going to dissipate? Well, we can use I is equal to V over R. So power is V squared over R, and that's 25 volts squared divided by R. If we have a 25 ohm resistor, we're going to get a watt of power. And a watt, well, is a lot. It will actually probably burn your resistor. If we have a 25 kilo ohm resistor, it's only a milliwatt of power. That's harmless. But where does this energy actually go? We're transferring energy, that's what a power is, so where is it going? Well, it turns out for resistors, what's happening is we're dissipating that in heat. We're driving electrons through this electronic lattice, as we discussed with Ohm's law, and heat is being generated as vibrations are caused in the lattice. There's other devices which are not resistive, in fact we call them reactive, for which the energy goes somewhere else. It goes to the fields, the electric and magnetic fields surrounding the component, and we can get it back. So it'll be temporarily stored in the fields and it'll go back into the current. And this has to do with the relationship between the voltage and the current in these devices. They're out of phase. We'll talk about that and reactive circuits in general in a couple weeks. A typical resistor, like this little one right here, typically has 1/4 of a watt or 1/8 of a watt of a power limit. If you want to drive more current through it, if you want to dissipate more power, this is one such example here. It's got a heat sink for a case, which is just designed to dissipate a lot of heat. And according to this, it can do 50 watts. So this one can dissipate a lot of heat. And they're usually used for testing loads as they're called. But what happens if we violate this wattage rule? This is an experimental physics course, so let's do an experiment. What we have here is an 1/8 of a watt 10 ohm resistor. Now 1/8 of a watt means that V squared over R is such that we can only put about a volt through this thing before exceeding its power. Let's see what happens if we try to put a lot more on there. Okay, so we have our resistor hooked up to our power supply. Voltage is set to 0. We're going to slowly increase it. And as we increase the voltage, current is going to start to flow as per Ohm's law. And very quickly, we're going to get above that 1 volt limit. Let's go well above it. And yes, as we can see, the magic smoke starts pouring out of the resistor. This is why we don't exceed the power rating. In fact, this is how heaters and incandescent light bulbs work. They work by glowing red hot by pumping a bunch of current through them. And there we are. So that's Joule's law, and that's how energy is dissipated in electronic circuits. In summary, we can always use the formula P is equal to IV. That is, whenever a current is flowing across a difference in potential, some energy is transferred. For ohmic materials, that is, materials that obey Ohm's law, we can write this a couple of different ways. We can write power is equal to V squared over R, or I squared R.